All right. Hello, everybody. Welcome to the Georgia Tech Graph Theory seminar. Our speaker today is Lina Li from University of Waterloo, and she will tell us about intersecting families of sets that are typically trivial.
Thank you, Anton. And thanks for the invitation, and thank all of you for coming to my talk. It's really my pleasure to give the talk in here, Georgia Tech. Yep, so today I'm talking about some recent progress on the intersecting family. And this is a joint work with József Balogh, my PhD advisor from UIUC, and Ramon, who is a second-year PhD student of UOG now, and Adam, who was a student of UOG and now he's in the Tel Aviv University as a postdoc. So it's a very international working group because UOG is now in the US, Ramon is in the Mexico, I'm in the Canada, and Adam is in the Israel. Very international. Okay, so let's start with some basic definitions. A K-uniform set family of n integers is intersecting if for every pair of the sets, they have a non-trivial intersection. And the trivial intersecting family, or in other words, the star, is just a family of all the sets that contain a fixed element. So this is quite a standard definition. And one of the cornerstone results related to this intersecting family is the following Adash-Corrado theorem from 1961. And they showed if you have a K-uniform intersecting family, then the size of this family is at most n-1 choose k-1. And in particular, this equality is only achieved by the trivial family, the stars, when n is at least 2k plus 1. Okay. So this is a very classical extremal type theorem. So once we know the extremal number, then the next natural thing is to ask how many intersecting families are they and can we describe the typical structure? Okay, so here we're going to use this I and K to denote the number of intersecting K-uniform intersecting family. And this line of study was initiated by Balogh-Das-Liu-Sharifzadeh-Tran in 2015. They first proved that when n is at least 2k plus 1, then the logarithm of this quantity is asymptotically n-1 choose k-1. And just to give you intuition on this quantity, so if you just think about the number of stars, so that is at least this many. So n is for the choices of that most common, the fixed elements, and then you can take arbitrary subfamily of the maximal stars, right? So if you look at this two quantity here, the difference is really on this arrow term here. So a natural question arises here is if this arrow term is really necessary, or in other words, which one is closer to the truth, this trivial lower bound or this upper bound. And the same group in the same paper, they first show that when n is at least 3k plus 8 log k, almost all the intersecting families are trivial. So in particularly, the number of them is asymptotically this many. So this is where the computation begins. So next in 2019, Balogh-Das-Liu-Sharifzadeh-Tran, they pushed the work forward by showing the same conclusion works for n is at least 2k plus this c root k log k. So previously it's 3k. Yeah, 3k plus log k. Now it's 2k, but with a root k. And around the same time, almost the same time, another group, Frankl-Kupavskii, they proved similar results with a stronger constant. So instead of c, they have a 2 here. And although this two paper appears in around the same time, but they use totally different method. The first group, they use a Das-Tran removal lemma for the families with disjoint pairs, which I will mention this result later. And the second group, what they did is they transferred this problem intersecting family to the problem of cross-intersecting family. And somehow the stability results on the cross-intersecting family is very helpful on pushing the work forward. Okay, So the main result I would like to present here is we are able to show when n is at least 2k plus 100 log k, the same conclusion holds. That is, almost all the intersecting families are trivial. So here we remove the restriction of root k. So that's the improvement. And in particular, this is equivalent to show the number of non-trivial family is sufficiently small, much smaller than this quantity. And the main tool we use is this Sapozhenko's graph container method plus the Das-Tran removal lemma. And so let me talk about the methodology a little bit. So as I just said, the main tool is this graph container lemma, which was developed by Sapozhenko in 1987 to give a very nice reproof of the following theorem, the number of independent sets in the hypercube. Just like all the container tools, the key idea here is for each independent set, we are able to assign a fingerprint to it, which determines a small container, such that the independent set is container. And most importantly, the number of such containers is also small. So once we have those containers, then instead of counting independent set directly, all we need to do is to give a bound on the number of independent set in each container. And this number is supposed to be small because now we have a much smaller container compared with the original ground set. That's where the saving comes from. Okay. So to apply this container idea for our problem, the first task is to build a bridge between the intersecting family and the independent set. And it turns out there is a very natural way to do that. Okay, so for simplicity, let's let n is equal to 2k plus r. And now we can assume this r is between 100 log k and this 2 times root k log k. So the lower bound is just from our assumption, and the upper bound just comes from when r is larger, it has already been proved by other group. Okay, so it saves some time. Now let's just take an arbitrary intersecting family, K uniform, and let F be the most frequent elements of it. That is the integers which appears in the most number of sets in this family. And without loss of generality, we can always assume this most frequent elements is the largest integer and it's symmetric anyway. And next, we're gonna split this set family into 2 parts. The first part consists of all the set which does not contain n. And also we're gonna take the complement in terms of this n minus 1. And now this is contained in this k plus r minus 1 uniform family of n minus 1 integers. And the rest of them, they are sets which does contain n. And because they all contain n, we can actually shrink this n here. So now B is a k minus 1 uniform set family from n minus 1 integers. And for simplicity, we denote this 2 set by L k plus r minus 1 and L k minus 1. And the reason we use this notation is this is actually 2 layers of the Boolean lattice. Okay. And next we define this auxiliary graph H, which is a bipartite graph defined on these 2 layers. And 2 sets are adjacent if and only if the set from top layer contains the set from bottom layer. So it's actually same as the adjacency in the Boolean lattice. Okay, so this is a very nice bipartite graph. Let's have some important observations. So the first observation is this H is a biregular bipartite graph. So for biregular, what I mean is, so we have this 2 layer. For all the vertices on the top layer, its degree is exactly the first quantity. And for all the vertices in the bottom layer, its degree is exactly the second quantity. So they, if you form the same part, they always have the same degree. Okay. So for the ease of notation, we denote this D to be the first degree. And actually, this graph is almost deregular in the sense that the second degree is asymptotically d. So this fraction, when r is much smaller than k, so it's asymptotically 1. Okay, so it's almost a regular graph. The second observation is this A, which is the part on the top layer. That's an intersecting family. So this is just come from the property of the intersecting. And most importantly, the second observation is A union B is an independent set. So this is also easy to get. So if it is not independent, then it must violate the intersecting property. Okay, so what this really tells us is we can find an injective map from the intersecting family to the independent sets, where we map this family to here the most frequent elements and this unique independent set A union B. Now, given this relationship, we can always jump back and forth between these two objects and study each other. And in particular,
may I ask a quick question at this point? So we have not used yet that f of this lowercase f of f is the most frequent element, right?
Yeah, so basically you should think about we have this n copies of this independent sets. Each copy is corresponding to a different most frequent elements. And by the symmetry, we just need to study one of them. Yeah, so basically in the final step, you will times n, but this factor is small enough to be ignored. Okay, right, so yeah, so once I have here, in particular, the number of independent sets will give an upper bound on the number of intersecting family. But they are not actually equal because, so whenever you take an independent set, it's not always that this A part is the intersecting family. So this is actually a larger class, but it's enough to give a very nice upper bound. Okay, so right. So next I'm gonna move to the real proof part. So a few more definitions. So for bipartite graph with classes x and y, and consider a subset of x, A. And we use this as the closure of A, which is we take all the vertices whose neighborhood is contained in the neighborhood of A. And so basically the relation is also if you have some A, and closure will be some set which contain A, but perhaps have more vertices. And the set is closed if the closure is equal to itself. Okay, and just recall from the previous page, we talk about this map. Okay, so it's the phi of f intersect the top layer is exactly those set who does not contain n. So the one which is not a okay, so who does not contain n, and also we take the complement. And we're gonna split the proof into two cases. The first case is when the closure of this intersection has large size, and the second is for smaller size. And we're gonna use totally different tools to deal with these two cases. Okay, let's start with the case one, the family with large closure. And the proof for this case is actually nice and short, so I will plan to go through in detail. So let's start with ML, which is a collection of maximal non-trivial intersecting family of size exactly this many. So maximal is a standard, so that is whenever you add a new set, it will violate the intersecting property. And here, basically, the L measures the distance from the extremal number. Okay, and take an arbitrary intersecting family with property 1, so that is has large closure. And we will take a maximal family F star, which contains this F. And there could be multiple choice, but it doesn't matter. You can just take arbitrary one. And most importantly, we're going to show that this F star is in some ML, where the L is larger than n times 2k choose k. So essentially what this part says, even if an intersecting family has large closure, but is sufficiently far from being extremal. And this is where we're going to use this removal lemma. Removal lemma says if F is an intersecting family of this size, so here this L times this binomial number is just corresponding to our L here. So it's the same thing here. So for such an intersecting family, there always exists a star. So S is a star, such that the symmetric difference of these two families is upper bounded. And in particular, you can always think about this as star is corresponding to the most frequent elements of F, because that will give you the minimum symmetric difference. So this symmetric difference is upper bounded. So here I want to remark that they actually prove it for a more general setting. So they prove it for any set family with given number of disjoint pairs. But here, because we are studying for intersecting family, where the disjoint pairs is equal to 0. So actually simplify this statement a lot, but they do have a more general form if you are interested. Okay, how to apply this removal lemma? So let's assume by contradiction that this L is actually smaller than what we want to prove. And then we apply this removal lemma on F star. And then we have this symmetric difference of F star and this larger star is upper bounded by this number. So just plug in this L. Okay. And the next thing, this inequality, it just simply comes from F is containing F star. So the symmetric difference is smaller. And then next, so this S star is actually corresponding to the most frequent elements of F star. And here, this S, I mean, is corresponding to the most frequent elements of F. So by the minimality, the symmetric difference here is smaller than the symmetric difference here. Okay. So now we give an upper bound on the symmetric difference of F and S. Okay. On the other hand, recall H is a biregular graph. So the size of the closure is upper bounded by the size of the neighborhood times the fraction of the degree, just by very simple double counting. So that's the first inequality. And the second inequality here comes from that, remember phi is an independent set. So its neighborhood has to be disjoint with itself. So, right, so here we have this two layers. Right, this set, let's call it X for now. X is here, so the neighborhood is in here, but it has to be disjoint with itself. So it must be in LK minus 1 minus phi of F. And this 2 just to give an upper bound on this fraction, which is not really important. Okay, then the next is, so if you recall the definition of this auxiliary graph, indeed this LK minus 1 layer just corresponding to this star S, because that is all the elements which does contain that most frequent elements. Okay, so this difference is indeed in the symmetric difference of F and S. And now from the previous step, we get the upper bound here. So now we get the upper bound on the size of the closure. But remember, in our assumption, we said this closure should be large, at least this many. And when R is at least 100 log K, this number is actually greater than the upper bound we just get from previous step, much larger. So this is a contradiction. Okay. So up to now, we have proved that each intersecting family with large closure is contained in some F star, which is in here. So L is sufficiently large, far from being extremal. And a very nice application of the Balogh-Bach set pair inequality shows that the number of maximal intersecting family is upper bounded by here. So when we put them together, we will get the number of intersecting family with large closure is upper bounded by, so here we first just fix one maximal family. then the number of subfamily is exactly this many. You just take all the subfamily and you sum over all the maximal family, right? And then using this upper bound, we get this number. And now this is much smaller than here, much smaller than the number of stars. So that is what we want to prove. Okay, so this finished case 1. And next is the remaining case, the family with small closures. And in this case, we actually will jump to the independent sets. So we indeed proved a slightly stronger theorem. That is the number of independent sets with non-empty closure. So this condition basically say we are counting the non-trivial family. And also the closure of this intersection has smaller size. So the number of such independent set is small. Okay, few more definition. So for a set in the top layer, we said this set is two-linked if the square graph induced on A is connected. So itself is always an independent set, but we want the square graph induced on A is connected graph. And the two-link component of some set is just a maximal two-link subset of X. Okay. And so here we're gonna use a container idea. So recall this auxiliary graph. We have this 2 layers. And let's just take an independent set and look at its intersection with top layer. So it's an independent set. But we can always decompose it into some two-link component. Let me use red. So I can decompose it into some two-link components. And those two-link components will be my fingerprint to represent this independent set. And then what is the corresponding container? This is actually easy. We can just construct directly because once you know this independent set must have those two-link components as its intersection, then on the other side, you can only take vertices from the non-neighborhood. And you can actually take any vertices from the non-neighborhood. So the container here will be, we first take the union of this fingerprint, because that's also my part of my independent set, plus whatever is not in the neighborhood. So now any independent set with this intersection must be contained in this container C. So this time is very special because we have a nice underlying graph. So we can actually manually construct this fingerprint and the container. But then now the task really is how do we count the number of a container? Okay. Yeah, oh, hey, so here I just summarize what I did before, define as container. So once we have those container, then the number of independent sets is, so you first fix one container. Then the number of independent sets containing that is exactly this many. So 2 to the size of the non-neighborhood, because you can choose arbitrary subset from the non-neighborhood. And then we sum over all possible containers. And remember, the goal here is to show this quantity is much smaller than this. Okay, now if you just look at this 2 side, so we have this 2 to the binomial, 2 to the binomial. So really, the crucial thing is if the saving from those forbidden neighborhood is large enough to counteract the cost of the containers. That is the crucial part of this comparison. And in other words, the heart of the problem is, given the size of the neighborhood, can we give a good enough upper bound on the number of choices for AI? So that is the heart of the problem. Okay, so again, just to recall you this auxiliary graph, bipartite graph, And we have AI on the top layer, which is a two-link set. So I mentioned before, this H is actually a subgraph of this Boolean lattice. So we all know Boolean lattice has very nice structural properties. And one of the nice thing is when AI is small, then the size of the neighborhood is much larger than the size of AI. So this is a good direction because this really says we're going to save a lot from the forbidden neighborhood. So in this case, we can be pretty general on the choice of AI. So that's the easy case. So basically, we just use a number of the choices for number of two-link sets, which is quite general upper bound. The difficulty is really when AI is large, especially the size of the neighborhood could be as large as itself. And now we didn't give a lot of saving from the neighborhood. So the comparison becomes very subtle. We have to be very careful on the choice of AI. And this is where we're going to use the Sapozhenko's graph container lemma. And in the next page, I present this lemma. It's very technical, pretty long, so I won't expect you to read it carefully. But instead, let me walk through you to see the main point of this technical lemma. So the goal of this statement is to give a container for this set family, this GAG, which is the collection of two-link sets with giving size closure and giving size neighborhood. So we fix the size and to see how many choices are they. Right? So if we have the container for that, we could use it to give an upper bound on this family, which will answer our question before. Okay. And this lemma says, okay, for this set family, we can find a collection of small containers. So this container is a pair of two sets. Here I put the small function because the formula is pretty long and technical, but we do have the precise formula. If you're interested, you can find in our paper, but here I would just skip the detail. Okay, so there is a function which map each candidate A to a pair of sets to our container S and F. And S and F satisfy the following property. So you can see the relation is I have an A closure here. And this will be S, which is containing A closure. And the neighborhood is an A. Oh. No, this way. An A, and F is contained in the neighborhood. So that's the location of the set S and F. And also the second condition basically says S is not too large compared with F. So basically this two property sets means this container is small in the sense that there are not so many A's associated to each SF pairs, because the size actually are pretty close here because of these two conditions. So that is the Sapozhenko's graph container lemma. The application of this lemma is not actually straightforward. It contains several technical tricks. So I don't plan to show the details here, but this is really the main idea here. So in the rest of the time, oh, how much time do I have?
You have about maybe 20 minutes.
Oh, I actually go very fast. Okay, never mind. Anyway, I didn't prepare the details, so let's go to the next part. Okay, so this is actually, I think, the most interesting part, also my favorite part, the open problems. So far we have proved that when n is at least 2k plus 100 log k, almost all the intersecting families are trivial, right? So the natural open question is what happened for smaller n? And we conjecture that when n is at least 2k plus 2, the same conclusion should work. And I can show the reason why we believe this should be the conjecture. So let's again, recall this bipartite graph H. So if you take a non-trivial intersecting family, that actually means there are some vertices on the top layer, because the lower layer is corresponding to the star, the trivial family. And we often call it here the flow, because that's the non-trivial part. Okay, so now let's just think about all the intersecting family with exactly one flow. And because n is at least 2k plus 2, so these two layers are a bit far. They are not consecutive. So the degree here is at least roughly k squared, in the order of k squared. Okay, so how to count the number of intersecting family with exactly one floor? We first pick the choices of this floor, which is m minus 1, choose k plus r minus 1, just the number of vertices on the top. And then the independent set, or the intersecting family, will be in the other side. We can only choose from the non-neighbor, which is minus k squared. Okay, and now this binomial number is upper bounded by 2 to the n, which is upper bounded by 2 to the 3k. Okay, but here we saved k squared vertices, which is much larger than the 3k here. So this quantity is much smaller than the number of trivial family. So now you see here, even with one floors, the number of intersecting family drops dramatically. And that is the main reason we believe the same conclusion should work for n is at least 2k plus 2. And here I would like to mention, so if you want to prove the conjecture, personally, I believe the bottleneck is really on the family with large closure. So let's go back a little bit since we have time. So here, so what stops us from proving like the constant or smaller term is really here we use a Balogh to give an upper bound on the number of maximal family. And so in order to counteract the cost here, we really need a large enough L here. So we didn't need to be very far enough from the extremal. And this is where we need a large R. So that is the obstacle here. So if you want to prove it for smaller n, so definitely some new ideas needed in this page. Okay. Right. Okay. Okay, so there is still one remaining case. That is when n is equal to 2k plus 1. And this is actually the most interesting case, because first, in this case, it is not true that almost all the intersecting family are trivial. We can actually construct a much larger family of them. Construction is similar. So now we have this, let's still take this bipartite graph. And now we actually have two consecutive layers, and the degree is roughly k. Okay. So to construct, the way is, let's first take an intersecting family on the top layer. Okay. And then it's pretty much like the reverse mapping of the mapping I mentioned before. So you take this intersecting family, and then you take some set B, which from the non-neighborhood. So this, and when you map it back, take the inverse, and it will become an intersecting family. Okay. And again, first let's think about when this A has size only 1. And the similar argument shows we can construct this many intersecting family. So the choice is for A, and you take the subset from the non-neighborhood. So similar argument, but now the difference is this binomial is roughly 2 to the 2k, but here we only saves k. So this quantity is already much larger than the number of trivial family. Okay, so now only with one floors, you will construct a lot of intersecting family, and more floors will also be allowed. And indeed, if you consider the random set of this size, 2k choose k times 2 to the negative k, and this is actually of order 2 to the k roughly. And by some standard probabilistic argument, you can show almost all such subsets are actually intersecting. It's a very simple probabilistic argument. And also you can use the probabilistic tool to get the estimation on the size of the neighborhood. So by the similar argument, we can show there are at least this many of intersecting family by this construction. So this formula here, this term is actually corresponding to the number of trivial family. But here we have those large actual term. And this exponent is pretty large in the sense the first term, an exponent is of order 2 to the k, and the second term is of order k to the 3/2, and then some minor term. Okay. So we really get a lot of intersecting family. So next, let me describe what we believe to be the typical structure, because we know the star is no longer typical. Okay. We said set family is nice if we take this phi of f, that independent set, and intersect with the top layer, if this intersection only have components of size 1 or 2. And by an application of the cluster expansion, which is a recent tool developed by Janssen Perkins, we can show the number of nice set family is this many. So I hope you feel this formula is familiar, because that's actually similar to the lower bound I just get. So again, this is the number of intersecting family. We have those actual term. This is exactly same term if you want to look. 2k choose k times 2 to the negative k. And the second term is also of order 2 to the 3/2. So it's very similar. The main difference between these two formula is, so here the coefficient between this k to the 3/2 is 1/2. So this is 1/2. But in the previous formula, the coefficient is this log 2 over 2. So that is the major difference between these two formula. And so we conjecture that when n is equal to 2k plus 1, then almost all the intersecting family are nice. So typically they should only have components of size 1 and 2 on the top layer. And also we believe the number of intersecting family is this many. So it's the same formula as before. The only thing is we put the theta here instead of the precise constant. The reason we put the theta is, so first, personally, I don't believe the constant from lower bound is the truth. So I don't think that's the correct constant. But also, I'm not sure if this 1/2 is the correct constant. So the reason is, so here, a nice family is not necessarily an intersecting family. Because if you just randomly took components of size 1 and 2, very likely you will get some disjoint pairs. So there could be some gap between. So maybe the truth is 1/2 or some numbers in between. Okay. And that is actually all I want to talk today. I go a little bit fast, but that's what all I have. Thank you for listening.
Thank you very much, Lina. Let us all thank the speaker. Are there any questions? I have a question, actually. Are there similar results not for non-uniform set families?
So I think, I don't quite remember, but maybe in the first paper, they do have some general results on the non-uniform intersecting family, but maybe not that tight result, because even for this uniform one, there are still question opening here.
Right. I was also curious about, so this proof that you presented only uses the graph containers method, right? Not the hyper, so like how, not the more sophisticated hypergraph versions. I wonder if one can do something even better using the hypergraph containers somehow.
So that's a very nice question. And indeed, the very first result, this one, they use the graph version of the hypergraph container method. So this Sapozhenko, they all call the container method, but it's actually quite different with the Kleitman's container and the hypergraph container. So the reason is its application is really restricted on the special graph. It has to be, now the application is only on the bipartite graph. And previously they used it for hypercube, which is a regular bipartite graph, and it can be easily extended to biregular one. And I also believe if your graph is almost bipartite, almost regular bipartite. Almost regular means the degree is in the small range. You can also use it to give perhaps a good bound. So, but the application is very specific. But the hypergraph container is more general. Right. But the sacrifice is you will get a weaker bound.
I see. That makes sense. Are there any more questions? If there are no more questions, then let us thank Lina again.